nitrate dioxide and an air pollutant in addition to greenhouse gases. Furthermore, it is recently pointed out it is important to consider the effects of short-lived climate forces, SLCFs, such as ozone and aerosols. Earth observations of GHGs and SLCFs should be able to contribute to the various goals of sustainable development through synergetic effects between climate change mitigation and air pollution countermeasures. I look forward to fruitful discussion on how Earth observations can guide policy and mitigation actions toward net zero. Ministry of the Environment, Japan, will continue to contribute to the implementation of the Paris Agreement and mitigation actions through GOSA series of observations. Thank you very much for your kind attention.
Thank you, Mitsani-san. So now we'll get into science talks. The first speaker will be Dr. Hiroshi Tanimoto. He's a co-chair of this event. Hiroshi is the Deputy Director of Earth System Division at NICE, and he's an expert of the air quality measurement and analysis. He's a co-lead of GOSA's GW project. So he'll be talking about an overview of this event, also setting up the stage for this discussion.
Thank you. First of all, thanks for coming to this important event. It is my great pleasure to be here in this COP event, and also great pleasure to start speaking like one of the kickoff speaker here today. So, as Tom said, this is a joint event between NICE and USRA, and NICE is specifically working for a better environment, and USRA is working for space research. But we share common interest in terms of emission mitigation. And you see that in the title of the seminar, it says for Paris climate goals and sustainable development goals. So climate goals is about climate. SDG is about we people, society, and ecosystem or whatever. So for me, mitigation is all about emissions. So today I'd like to talk about how Earth observations is critically playing an important role in better understanding of emissions and for mitigation actions. I believe the better understanding is really critical for better actions for mitigations. For whatever species, I'm saying whatever species, whatever emissions, not only greenhouse gases, sugar, climate forces, air pollutants, like Mr. Mitsani said. So let me start with showing you kind of a promotion video of our strategic research program at NICE starting in 2021. We have a sound, but it's okay. Never mind. Just have a look. Oh, thank you. Thank you. That's great. Thanks. So as I said, we started this strategic research program at NICE in 2021 and for 5 years, and it's the climate change and air quality research program at NICE. So this is one of the 8 strategic research programs, and the overall objective is to provide scientific basis toward global stabilization for climate change and air quality issues. So we have 3 projects. And then one of these is to better understand the natural carbon cycle. Second one is more focused on urban city, urban scale, national scale emissions, particularly anthropogenic emissions. Third project is focusing on modeling but not only climate modeling, but also air quality modeling as well. So we really think together greenhouse gases and air pollutants in terms of observations and modeling for the better reconciliation of the past trends and also future predictions. But key thing is here, what is that? It doesn't work. Emissions inventory, in particular evaluations and improvement in the really center. And we see projects working together. So that's the kind of key thing here. So the question is how Earth observation can help emission estimates, or how we can know emissions are better. So I know in all over the world, many institutions are putting so much effort in making better measurements. We, National Institute for Environmental Studies, we're putting so much effort in terms of in getting good measurements in the Asia and Pacific regions. One of these is ground-based observations, of course, in Hokkaido, Okinawa, and also top of Mount Fuji, and also in downtown Tokyo. And we also do aircraft measurements with Japan Airlines, and also we are collaborating with cargo ship companies. They put instruments and between Japan, North America, Japan, Australia, Japan, Southeast Asian countries. And of course, we are putting so much effort to the space observations called GOSAT. First one, second one, and third one is coming up in space next year. So how we can make it better? So we're putting these a lot of observations, high quality observations into the high resolution models, as models are going toward high resolution, as you can see in this video. Right? So then we can get high resolution flux estimates of carbon CO2 on carbon cycles in global scale, like this. So now, previously, it was like a 2 degrees, something like that, but now we can get estimates at the spatial resolution of 1 by 1 degrees. So, of course, all of these efforts are scientific efforts, but we are really keen to input our global stocktake processes and broader policy contributions processes. So we're publishing this bulletin of multi-scale estimation of greenhouse gas budgets back in, I think, last year, and then updating every year. So just have a look, just search on the internet and get one and have a quick look. So I'd like to change gear a little bit to short-lived species from now, in particular like a black carbon as a good example in talking about emissions trends. Black carbon is different from CO2. As you see here, a lot of emissions are from East Asia. Right? On the right panel, East Asian emissions of black carbon are really increasing over the last couple of decades. And that's also important for global climate and also Arctic climate and the environment as air pollutants. So here, but emission estimates of these black carbons are really tough. You see here, a lot of estimates. CDS was used for IPCC models, and Eclipse was used for Arctic climate assessments. And other community emissions inventory are there. And one of these are high, one of these are low. And you can see spread is really by a factor of 2 over the last 20 years. So that's really huge, right? And one emission inventory is predicting going up, and another emissions inventory is predicting going down, right? As emissions are really changing, right? Because we are really implementing the mitigation processes. But as observations, atmospheric observation can help in better constraining these emissions inventories. And we did it by using observations in Japanese, well, surface observations in this case. So here, you can compare this, and that's red lines show top-down constraints of black carbon, top-down estimates of black carbon from China. Right? So it's really decreasing, and lower end. That's kind of contrasting to the bottom-up emissions estimates. And important here is like future scenarios are based on the latest past emissions inventory. But if we didn't get the current emission inventory wrong, then future scenarios get wrong. So that's a kind of important message. Okay, and climate impact is also kind of substantial, not only necessarily huge, but also we see substantial impacts. for the East Asian climate in this case. So I'd like to again emphasize knowing emissions is really critical to better mitigation and also better prediction for the future. Okay, thanks a lot. And I'm happy to take any questions later and in panel discussions. Thank you.
Thank you, Hiroshi. Right, this wonderful talk. So we just realized that we haven't shown this slide we prepared. So like I mentioned earlier, we have a great speaker today, and myself also Hiroshi will be chairing, also the 5 speakers from Science Talks. And so if you have a question, here's an email address, so we are collecting your question and comment same time. We have probably have time to take a question later on, but if you're not, just send an email to us, and we are trying to address a question later on. Right, so next slide, please. Then again, we did prepare this slide. Right. Okay, so let me introduce the next speaker, who is Dr. Oksana Tarasova from World Meteorological Organization. Oksana is the senior scientific officer at infrastructure division at WMO. She's been working on lots of the frameworks, which is such as the Global Atmosphere Watch, also the ongoing Global Greenhouse Gas Watch, G3W. I want to ask you to speak about the international perspective, what you expect for the Earth observation. By the way, Oksana has a great TED Talk. If you're interested in it, please check it out online.
No pressure. Okay. Fantastic. Thank you so much for the invitation. It's a great pleasure actually for me to speak on this event, because the collaboration with the Japanese colleagues is really amazing. They support a lot of the work which is done within the international community. And I will talk about the role of Earth observations in support of climate mitigation. So what is it what the stakeholders want to know when they come to the mitigation table? It is important to understand that they have multiple requests. So when they come to the mitigation, they actually want to know what is the current state of the emissions on a common baseline. And that is a problem at this point, because many non-Annex I countries, when they were exposed to Paris Agreement, they don't have established inventory. They have the national reports, which actually are far beyond the inventory when it should be. The second point is that, of course, we want to know what is the sectoral and spatial distribution of the emissions, because when you take actions, you wanted to know where to act and how much you actually can cut. But what is even more important, and which is not part of inventory, is that we would like to see the response in atmospheric concentrations to the actions which has been taken. Because at the end of the day, it's a concentration of greenhouse gases in the atmosphere, which is driving the climate change. But also when you plan your mitigation forward, you would like to know how the concentrations of greenhouse gases will change in the future, not only in response to your emissions, but also given that many of the emissions are coming from natural system, and you wanted to understand the climate feedback, which actually impacts those emissions. So there are 4 different pieces of information which the person who comes to the mitigation wanted to know to have their country on a safe ground. And the point is that you all want to know this information, which is provided on routine and sustained basis. So it's not a one-time exercise. It should be routine and sustained basis. And that should be produced following the international standards. You don't want it to all have mitigation on a different basis. We need international standards. But also you would like this information, being on international standards, to be tailored to the needs of the community which you represent. If you are the farmer, you're not interested in national total, you are interested in contribution of a specific sector. So when you produce this information going from the globally, nationally regulated things, you want to also to have the tailored products which would support your mitigation strategy. And currently we are in a situation that the information on a common basis is not largely available, for example, for Annex I country. Given that the response of the concentration to the natural or climate change, and given that information is not available, WMO members approved at the Congress this year, 193 nations, approved a system which is called Global Greenhouse Gas Watch. So the purpose of the system is actually fill this gap in the information which is available to the member countries and develop the system which will provide on a routine, sustained basis with a minimum possible delay, monthly net fluxes with a resolution of 1 by 1 degree, the main greenhouse gases, methane and CO2, and looking also at opportunities to produce those monthly fluxes and concentrations of N2O as well. And that will be the system which is pretty similar to the numerical weather prediction, where you have several participating modeling centers that produce this type of the product. And one of the centers will be supported by NIAS. So one of the centers which we will be collaborating in this exercise will be the institution, and we've seen in the presentation of Hiroshi that this center is producing these 1 by 1 degree products. So what are the key elements? How can we actually deliver this product on a global scale? There are several elements which we need to take into consideration. And the first one is the observing system. So this system will not fly if you don't have observations. And you need to have observations from the ground, from the aircraft, from the satellite, and not only for greenhouse gases, but also for meteorological parameters and for the other variables which will help you to constrain terrestrial fluxes, anthropogenic fluxes, or ocean fluxes. You need a lot of prior information. We need inventory. We need advanced scientific inventories which would fit in the system. And then we combine all this information for the modeling system to produce the 1 by 1 degree product by several centers. What is the role of the Earth observation here? Well, the satellite agencies, when they participate in this exercise, we would like them to share as much information as possible and as fast as possible. Because there's a lot of information which has been produced by the satellite agency which is not openly shared, and we would like to ensure that this is sustained and openly shared. And what can we do with this information? I mean, you can say 1 by 1 degree is not a super useful product. Indeed, but it allows us to create a whole chain of the added value products. First, you can actually aggregate this product and create a direct contribution to the global stocktake. That will give you the global total on a monthly basis. You can also aggregate this product on a national scale, so you can actually aggregate the grid boxes which cover your nation and give a first glimpse of what are the net fluxes over the specific territory or specific region. But you also can create a whole chain of the different products that would be higher resolution products, the national specific products, the tailored products for the specific sectors if you go with the attribution, and you have to do it following common practices. And we have the Integrated Global Greenhouse Gas Information System, IGIS, which actually helps to establish such practices on the post-processing of the products and creation of those added value products. And though creation of such a product is not directly in the scope of Global Greenhouse Gas Watch, we are actually working to make the connection with the service component. And we started development of the implementation plan for such system, which has been asked by Congress for us to do. And Earth observations are the part of this plan. And to understand what is the status of the Earth observations, or what is the status of the input, we conducted a very big workshop in October this month, which actually looked at what are the critical gaps that would need to be filled in to allow us to move with implementation of the system. And of course, there are traditional special temporal gaps which need to be filled, like Arctic, tropical regions. But also there is a validation gap, like do we have the system on the ground to validate the satellites? Do we have the continuity of the missions or continuity of the specific data sets in the future, which creates the concerns for the operational system, because you cannot actually discontinue the source of information. We also identified that there is a financial gap, so somebody has to pay for the implementation of the system, and we are looking at the financial mechanisms. But there's also a substantial manpower gap. I mean, we don't have enough scientists actually to make the measurements. In most of the countries in the world, people actually don't know how to make measurements of greenhouse gases. Or they don't know how to use the data. Or if you talk to policymakers and you say, here is a map of the fluxes, and they say, so what? So how to put it in a policy context? So there is no capacity to actually produce the data and use the data. So we need to do the capacity development. And we also need to look at the communication gap. What does this gap, what do this data mean and how you can use them? And here, the satellite community and the Earth observation community can help in addressing special gaps, doing the missions, establishing the sustainability of the missions so that we have an appropriate planning for the operational product, and also help us to communicate that it's not one or the other, it's the integrated system which we want from the satellite, from the ground, that can actually help to implement Global Greenhouse Gas Watch. Thank you very much.
Thank you, Oksana. Appreciate it. So now we're curious about this is a sort of what actually our science data need to be responsive to some needs here. And the next speaker, Dr. Tazu Saiki, she's an expert of the CO2 as a methane inversion analysis. She'll be presenting sort of contribution goals that have been made this past almost close to 1.5 decades, and also sort of new sciences happening in this project. Saiki-san, please.
Thank you, Tom. So, hello everyone. I'm Tazu Saiki from Satellite Observation Center, National Institute for Environmental Studies. Hiroshi and Oksana talked about the importance of satellite observation, satellites as greenhouse gas observation platform. So here, I'd like to introduce you about our research activities on Japan's GOSAT satellite series. So GOSAT is the world's first satellite dedicated to greenhouse gas monitoring from space. We have 2 satellites on the orbit now, GOSAT since 2009 and GOSAT-2 since 2018. And we are preparing for the next satellite, GOSAT-G to be launched next fiscal year. So Yusumiya is talking about GOSAT-G later, so my talk focuses on current activities on GOSAT and GOSAT-2. Next. So, what is GOSAT series? GOSAT is, What is GOSAT series? GOSAT is a Japanese Earth observation satellite series for measuring the greenhouse gases from space. So GOSAT was launched in 2009 and is still active and healthy. It equips FTS, Fourier transform spectrometer, to observe mainly CO2 and methane, CH4. And our second satellite, GOSAT-2, was launched in 2018 and also still healthy. It observed CO2 and CH4 and CO, carbon monoxide too, as a proxy of anthropogenic and natural combustion. FTS sensor has now has new functions such as intelligent pointing systems. The third satellite, GOSAT-G, is to be launched in fiscal year 2024. The measuring method is changed to an image spectrometer to observe CO2 and CH4 and NO2. So about organizations, the GOSAT series is a joint effort by MOE, Ministry of the Environment Japan, NIS, National Institute for Environmental Studies, and JAXA, Japan Aerospace Agency, Exploration Agency. The Satellite Observation Center SOC of NIS is responsible for generation, validation, distribution, and archiving of gas concentrations as levels per product, and estimated flux data as level for products, and so on. For these purposes, NIS has installed several TCON sites in Japan and the Philippines. And we have developed and operated 3 ground systems to process GOSAT and to open to product to public. Under domestic and foreign collaborations, we have the science team by domestic scientists. And also we have collaboration agreement with foreign space agencies. Also, we welcome participation of overseas researchers via GOSAT-3's research announcement RA. So here is an example of our products, GOSAT FTA shortwave infrared, SWIR, level 2 XCO2 and XCH4 concentration products. Since April 2009 to current, this is the world's longest record of CO2 and CH4 concentration from satellites. Upper panels are for CO2 and the lower for CH4. The data covers most of the world. The figure is for October 2023, and the blank area in northern high latitude is covered in the northern summer season, so the GOSAT observe whole Earth areas. Based on this, the L2 data, we produce CO2 and CH4 fluxes for inversion analysis and the simulated concentrations on L4A and L4B respectively. You can find these plots and products on our website written here. So these products have been used in worldwide research activities. So next. Here is application of GOSAT data. We also provide whole atmosphere CO2 and methane concentration based on our analysis of level 2 products. Here is an example of a CH4 methane case. The satellite observed the increased trend of the CH4 since 2009, and particularly the recent large annual enhancement in 2021. The cause of this sudden enhancement is still unclear and hot research topics. Anyway, GOSAT did successfully capture the change in the CH4 cycle due to anthropogenic and/or natural source and things. Paul will talk later about this phenomena in the next talk. So one more research topic from our research member is country scale analysis of methane emissions with high resolution inverse modeling using GOSAT data, GOSAT and surface observations. The global inversion analysis is conducted at a resolution of 10 kilometers biweekly, and now we can estimate methane emissions of the world countries such as China, USA, Russia, Brazil, and so on. So next, GOSAT 2. For GOSAT 2, we provide two products of GHG with two methods. One is flow physics method. The product by flow physics method contains CO2 and CH4 and new data CO. Proxy method, another method product, is contained CH4 and CO, and one more new parameter, the solar-induced chlorophyll fluorescence shift, which is expected to reflect land biosphere activities, that is GPP, gross primary productivity. We have more than GOSAT, the data number of the GOSAT 2 is more than those GOSAT observations. So L4 products is coming soon. So important results from our research team is written in the bottom of the slide. GHG concentration from GOSAT and GOSAT 2 were compared to evaluate their quality and found that the data of both satellites are generally consistent within 1% with slight regional differences. So now you can use both GOSAT and GOSAT 2 data for CO2 and CH4 together within 1% differences. And we also contribute to the global stocktake. We submitted our data, GOSAT and GOSAT 2 data to the first global stocktake, as written here. So last slide. GOSAT 3 data available on our NICE's website here. We prepare lots of content to help you. You can download the data freely, free of charge from our website after registering your valid email address. So we are now developing a website for next satellite, GOSAT GW, to provide the product to you. It is to be opened next fiscal year. So we welcome you to visit our website. Thank you very much.
Thank you, Saki-san. It's great to see the continued observation from GOSAT mission and that already providing super useful information for the frameworks that the Oksana illustrated earlier. So now I wanted to introduce Professor Paul Palmer. Paul is a professor at School of Geosciences, University of Edinburgh in the UK. He's an expert of carbon cycle, also air quality studies, and also he has been studying heavy user of GOSAT dataset. And he'll be speaking about some results from GOSAT, also using some other observations and how he can inform the public using satellite observation. Paul?
Okay, thank you very much. It's a pleasure to be here, especially since GOSAT has played such a key role in my research over the last decade or so. So, when the slides are up. Okay, so I'll go straight to the next slide. Okay, so this is a slide data that you should be familiar with. This on the left-hand side is the trace of atmospheric methane since the 1980s when it started being measured by NOAA. And you can see there's various points there where it's leveled off. So in the early 2000s, it leveled off. We do not understand why it leveled off because the data is insufficient coverage. And it started to increase since 2007, and now it's accelerating. I won't show you the NOAA data because, but what you'll see is that most of the data are in the northern hemisphere. There's a few points in the tropics, but mostly it's in the northern hemisphere, northern middle latitudes in particular. The striking thing here on the right-hand side is the growth rates, and you can see, and I'm going to focus on the late 2000s. Okay, so from 2007 onwards, you see the atmospheric growth rate increase. We now have record rates of atmospheric growth of methane. The 2020 and 2021, it's the largest value right now, and 2022 is large, and this has been revised, and 2023 it looks like it's going to be another a record year. So the focus of this talk is going to be 2009 onwards when GOSAT was launched. This is the start of the records. It allows us to understand a bit more about this, this record and why we are seeing these atmospheric growth rates. So the other thing I wanted to point out at this stage of the presentation was the fact that Japan has played such a key role in understanding atmospheric methane from space. So what I've shown you here, this is satellite data provided by Michael Buchwitz from the University of Bremen. He's tied together all the data from different kinds of data. So we have methane on the y-axis and year on the x-axis. And so apart from Skiamaki's start of the 2000s, which wasn't intended to measure methane, Japan has launched 2 satellites, and GOSAT has really been fundamental in our understanding of atmospheric methane and the emissions that are responsible for those changes. And we can see that TROPAMI was launched 2017, 2018. That's helped to complement GOSAT, and we start to get to better understand what's going on there. The other thing I should point out, so these are global survey instruments. There's a yellow line at the bottom there. These are hotspot mappers. You're starting to see different sensors providing very high-resolution information about individual assets, individual sources of methane. So we collect atmospheric methane. That is just the start of the challenge that faces us. So we have to turn that into emission estimates. And the way we do that is something called inverse modeling. And it's simply this. So we have prior emission estimates, which we interpret through atmospheric chemistry transport models, which predict concentrations, which we can then compare to the satellite observations in this case. And what we're doing is just fitting the model to the satellite data. It's a least squares fit is the simplest way of putting this. And what you end up with is emission estimates which are consistent with the prior emission estimates and also the atmospheric data and some uncertainties. So when you do that, you come up with all kinds of fancy maps. What I'm showing you here is a summary of what we found for 2020 and 2021. So on the top here is the large-scale regions that we're looking at. Okay, they're very large scale, just to simplify the situation. On the the bottom plot here, this is teragrams of methane per year, and on the y-axis you can see all those different regions. And the blue and the red bars are the emission estimates relative to 2019. So blue is 2020 relative to 2019, and red is 2021 relative to 2019. And what stands out here is East Africa. East Africa is a very large source of methane, and it's a source of methane from natural methane, from wetlands, which I'll talk about in a minute. You can see there's other different regions making a difference there, so tropical South America, but really East Africa is the dominant one. And this is just the latest chapter in a story that we've been telling over the last 5 years or so. What we find is that when we looked at, initially we looked at data from the launch of GOSAT to 2016, and we found that all the prior emission estimates of methane were wrong. Instead of what we thought was the Congo Basin emitting methane, we found that there was a very large emission source in South Sudan called the Sud. It's a Sud wetland, it's a very large wetland. And the middle plot is the methane emissions you can see that yellow line there. And then we have that dashed line there, that is the White Nile river basin, so the White Nile water level, and I'll come back to that in a moment because water plays an incredibly important role in determining the year-to-year change in methane emissions over this region. On the the right-hand side panel, this is a comparison of GOSAT emission estimates over that region and emission estimates inferred from TROPOMI. And TROPOMI was that second instrument that was launched in 2019. And what you see is they're tracking together. So that's great. So there's two instruments providing exactly the same kind of information, leading us to the same conclusion. And what that conclusion is that what water is being collected in Lake Victoria and it's making its way down the White Nile, and where it's ending up is the Sud wetlands. And I've talked about methane emissions, but of course we also have to bring in all kinds of other information to interpret that data. So this is work on by Andy Hardy. On the left-hand side, you can see a map. This is the Sud wetlands. If you can just to make out that yellow splodge in the middle, that's what it typically is, somewhere between 1980 and 2022. And the red is the size of the wetland in 2022. Okay, so typically it's that yellow. It can be a bit of the blue, but you can see the enormity of that wetland when it gets flooded. It's enormous. And that middle plot here, that's just a bar graph showing you that it has increased dramatically. And for many of the years, recent years, it's played a significant role in the global atmospheric growth rate of methane, of the order of about a third. The two panels on the right, I wanted to bring in the fact that all this information is great. We're all scientists, et cetera, but it has humanitarian impacts. We are seeing huge floods over this region, and methane's one signal, but we're displacing millions of people. There are wide-scale humanitarian impacts, including not just displacement, but also loss of agriculture. There's waterborne disease that are affecting a lot of people in this area. This is my last slide, and it supports some of the earlier speakers. So GOSAT, we talked about science, that's great, but GOSAT data is now being increasingly used as a policy tool. And in this case, we've already seen some examples where GOSAT data is being used to support the global stocktake. What we have on the left-hand side is the Copernicus, the measurement verification system that we're building. Observations on the left-hand side, they are incredibly important in trying to inform the decision support system, the information, the actual information that's going to be used for governments to reduce their emissions. And the right-hand side is just an example from a paper from John Warden showing 2019 emissions on a one-by-one grid, and that supports some of the other work that NISA have shown as well. So this is my last slide, just to re-emphasize GOSAT data, incredibly important for understanding methane emissions on a global scale, but it also provides incredibly detailed information about science on the regional scale as well. Thanks.
Thank you so much, Paul. It was a great example that we can inform greenhouse gas mitigation, but more, we inform what's happening in this world, then especially on the challenges we face. So I'd like to invite online speaker, which is Dr. George Hart. George is a professor at Department of Geographic Science, the University Maryland College Park, And just the online speaker, then this happened actually again. He was also speaking for us for our COP27 event. Thank you, George, for being here. So the after poll, George is notably leading NASA's carbon monitoring system program, where so many actionable remote sensing-based products are being developed. So we like to ask George to share his work, also some of the kind of experiences of using Earth observation for informing the public. So George, thank you for being here. Then also, I know you're on travel. Then also a couple technical issues as well. So can you hear me? Then.
Yes, thank you very much. Yes, thank you very much. You can hear me?
Perfectly.
I hope so. Excellent. So we can go ahead. What I'm going to talk about today is a particular example of some of the latest work coming out of the NASA carbon monitoring system, focused on forest carbon monitoring that we're doing for climate mitigation baseline, future planning and assessment. So next slide. So just to orient you, we're talking about focusing on the global carbon cycle, and in particular, this part of it, the terrestrial part of the global carbon cycle, where you can see that terrestrial carbon emissions are quite large on a gross basis, and on a net basis, offset something like 30% of anthropogenic emissions. So we need to make sure that we understand this carbon uptake in terrestrial ecosystems, where it is, what's causing it, and importantly, will it continue? And are there steps we can take to help make it continue or even grow it? So next slide, please. So one of the big advance I want to focus on today is from the EO side is LiDAR remote sensing. LiDAR remote sensing is really a qualitative change in our ability to do terrestrial carbon research. This is an active remote sensing measurement illustrated here from an aircraft cartoon, but an active pulse of energy down to the surface, which can measure the structure of the surface quite accurately using LiDAR, a backscatter technology. So you can think of it as a topographic measurement of the surface where we actually want the vegetation part of the topography. So we have two major orbital instruments collecting these data. Currently, the JEDI instrument, which is on the International Space Station, that collected data for over 2 years and is now in storage, hoping to come back out of storage later next year. We also have the ISAT-2 satellite producing measurements of this type globally. So we take these EO observations and use them in a state-of-the-art process-based forest ecosystem model. Now this model is tracking the individual tree statistics globally and all the processes that affect forests like growth and respiration, also disturbances and recovery processes as well. So when we marry these two sources together, this unprecedented data on vegetation structure and this process-based model, we think we are setting ourselves up to make significant advances on this term in the carbon cycle. So next slide. So a recent study published earlier this year showed that when we take these measurements, we can see them in the top panel. That's a global map of vegetation height structure from these two different EO platforms, with the tall vegetation shown in red and shorter vegetation in blues and whites. Here mapped at 1 kilometer spatial resolution. So this is very high spatial resolution for global carbon cycle studies, which typically are about half by half degree resolution. So we can take these same measurements and initialize our process-based ecosystem model to produce a baseline map of forest carbon stocks above ground on the planet. That's shown in the middle map. And For ecosystem modeling at a global scale, this is unprecedented detail. You can see patterns of clear patterns of human influence through deforestation and recovery and the like in these maps. So we believe these are very important for baseline purposes. The next bottom map shows that when we use those measurements to initialize our ecosystem model, it provides a very important constraint on those model predicted fluxes. So that's just 1 year of model predicted fluxes having been initialized from that model. So these are high resolution terrestrial carbon fluxes that the resolution of these EO measurements. We go through a heavy validation process. Here's some examples. The top scatter plot shows this process-based models, baseline above ground biomass estimates compared to the JEDI mission's own empirical estimates of forest biomass. The bottom panel shows a comparison of these same ecosystem model initialized measurements to the United States Forest Inventory Assessment data set just over that country. That's an unprecedented quality ground truth data set. And on the top right, just as another example, we can show these baseline estimates, again, available at 1 kilometer resolution, but aggregated to the country scale and compared to the recent FAO 2020 estimates for countries around the world. Okay, so this is good baseline mapping at unprecedented spatial resolution. But if I go take it one more step to the next slide, we can then use this information to inform planning. And if it works, Tom can activate the animation. What this animation shows is we take that same initialized map and we can run this model forward in time, having been initialized with these measurements, to understand how much potential future carbon storage there is in the world's landscapes. The green time series plot shows the current forest tree cover and what its potential to sequester additional carbon is in the future. The orange time series plot shows that would be new tree cover. So if new tree cover was allowed to be planted around the world, the potential carbon storage for that. And the blue is the sum of the two. And what you could see is that we have the potential to double forest carbon storage on the planet. And about a third of that potential is in existing tree cover, and about 2/3 would be in new tree cover. So next slide, and I'll almost done. You can advance one more, thank you. All right, so you may be curious about climate change. So we can take these same simulations and test them with different climate future scenarios. So what you can see in this panel is the histogram of gains or losses of carbon sequestration potential compared to the reference with different climate change scenarios going down on this chart. The current tree cover is on the left column and the new tree cover is on the right column. And what these histograms show is that the effect of climate change on forest carbon sequestration will be quite spatially heterogeneous, and there will be places that actually lose their ability to sequester carbon, and we believe even more places where there's going to be gains in the ability to store carbon. But it's going to be a quite spatially heterogeneous future. So I'll end with that. Thank you very much.
Thank you again, George. We have a panel discussion later on, so please stick with us a little bit more. Right, so now I'd like to invite the last speaker, science speaker, who is Dr. Yu Sommer. Right. So He's one of the young scientists in the GOSAT mission, and he's working on the greenhouse gas retrieval, and he'll be talking about what's going to happen next in the GOSAT mission, which is GOSAT times 3.
Thank you, Tom. I'm Yusumi from the National Institute for Environmental Studies, Japan. I'm talking about new insights provided by Chance 3 on GOSAT GW. Currently, the satellite measurement is very powerful tool for monitoring greenhouse gas concentrations or their emissions. The third generation of GOSAT GW, has a wider swath and smaller pixels than that of those of the currently operated satellite GOSAT and GOSAT 2. There are three mission objectives of GOSAT GW. One is the monitoring of the global mean concentration of greenhouse gases. These plots are the global mean concentrations of CO2 and methane obtained from GOSAT. The second one is the evaluation of national or country-specific anthropogenic emission inventory of greenhouse gases. The third one is detection of greenhouse gas emission from large emission sources such as megacities, power plants, and the natural sources such as permafrost. This is the specification of GOSAT GW. GOSAT GW will be launched next financial year. The orbit and release cycle is similar to those of GOSAT. The instrument called TAN3 has three target species, CO2, methane, and NO2. TAN3 has two observation modes, wide and focus mode. Wide figure is the conversion of swath and pixel sizes of GOSAT GW with GOSAT 2 and OCO2. The wide mode of GOSAT GW has a very wide swath of more than 900 km with a pixel size of 10 km, which is similar size of GOSAT and GOSAT 2. The focus mode has a smaller pixel size of basically 3 km and a relatively wide swath, 90 km, which is wider than the similar pixel size satellite OCO2. The wide mode is used for global observation. The wide mode enables us to monitor greenhouse gas and NO2 concentration immediately, like torpomi. Wide figure is an example of CH4 emission sources depicted by torpomi measurement. GOSAT GW wide mode has a ability to monitor CO2 in addition to methane immediately, like this image. The large point sources can be detected by wide mode globally. Left figure is the coverage of wide mode. This mode covers globally in 3 days. The focus mode is used to evaluate the emission of greenhouse gases with smaller pixel size. This mode can focus the C40 cities in 3 days, which is a release cycle. The left figure is the example of switch of wide mode and focus mode. In this example, the focus mode focuses on the Tokyo metropolitan area. The right two figures are the observation example, the simulated observation example of NO2. The focus mode can monitor the emission sources like this, detected sources detected by the wide mode. The left figure is a simulated concentration from the power plant near Tokyo. And the right figure is the example of retrieval against the simulated concentration. You can see that the focus mode detects the plume from the power plant of NO2. NO2 are plume. to quantify the greenhouse gas emissions from the satellite measurement, we have to identify the enhanced plume of greenhouse gases. Left here is the example of collocated observation of CO2 and troponin. The troponin NO2 was plotted in the background, and CO2 concentrations obtained from OCO3 is plotted over the troponin measurement. In this picture, the CO2 measurement, CO2 concentration, the enhanced CO2 concentration is difficult to identify because the CO2 concentration is relatively high in the background due to its long lifetime in the atmosphere. On the other hand, NO2 has a very small concentration in the background level, so the emission plume of NO2 is easily identified by the satellite, like this image. The TAN3 observes CO2 and CO2, methane, and NO2 simultaneously with the same field of view. Right here is the example of simultaneous observation of CO2 and NO2 by aircraft measurement. So TAN3 improves the accuracy of greenhouse gas emission estimates. Thank you for your attention.
Right. Thank you so much. Right. Now we move on to the panel discussion, and my co-chair Hiroshi will be chairing it.
Thank you. We really had excellent talks, summarizing and putting together everything. Then we're going to move to the panel discussion for, I don't know, remaining 30 minutes, maybe 25 minutes. And screen's off. Good. So I don't know. We can discuss whatever we want, but if you have any urgent questions, I can pick up, but if not, I can start saying something, questioning key questions to speakers. Yes, go ahead. Thank you.
Thank you all for the very interesting presentations. I was really intrigued by the point in Paul's presentation about the tropical methane. So we've heard for a long time this narrative that with climate change and warming in the Arctic, we might expect to see huge amounts of methane coming off in the Arctic. But in fact, what you showed and what we've been hearing for a while now is that we're actually seeing this increase in methane in the tropics. And what you showed is that increase in the methane in the tropics might also be related to climate change. So a climate change feedback. So I wondered if you could comment on that. And also, we've heard a lot at this meeting about the Global Methane Pledge, and that has this real focus on reducing methane from oil and gas, whereas in fact what the observations are showing is that the really big problem that we have is these natural and agricultural methane sources. So I just wonder if the panel can comment on those things.
Yeah, I think it's coming. Is it on? No.
Okay. Okay. So we are seeing, there is substantial evidence that Africa, East Africa in particular, the emissions from that region are increasing with time. And what I didn't have time to talk about today is that this is driven by a climate variability mode called the Indian Ocean Dipole, which would affect you probably as well. There's SST variations over the Indian Ocean, and when there's in positive phase, it dumps huge amounts of rainfall over Lake Victoria and other catchments, which make their way down to the wetlands. What's of concern is that the timescales of the hydrology mean that you get an immediate pulse of the SUD, at the side, but there's also a mode of variability that takes a couple of years to get to the side. So you get this continual emission of methane even after you get this Indian Ocean dipole. What we found is that the climate projections are suggesting that in the future there is a mode that IOD, Indian Ocean dipole, will be more like the positive phase as we go forward, and that is driven by increased levels of atmospheric greenhouse gases. So there's a greenhouse gas signature to that. So tropics, great. That's a challenge we have to face. It is what it is right now. The Arctic, there is also evidence that the Arctic is emitting larger amounts of methane, particularly in the last 10 years or so. But what that means is the methane pledge is even more important, and we have to double down on our commitments to reduce anthropogenic emissions. So, once the microbes grab hold of that, their ability to emit methane, then we have to really spend a lot of time figuring out how to reduce agricultural emissions without compromising food security, for instance, and definitely reduce emissions from oil and gas in one way or another. Does that answer your question? No?
Yes, go ahead.
Hello. Thank you for the great presentation. I know the last presentation talked about water cycle as well, and I work with rainfall, so I wanted to see if there were any data sets that were associated with precipitation patterns.
You mean water cycle product?
Yeah, so are there any data sets that are like they're looking at the carbon and the methane emissions? Are there any ones that are recording precipitation data?
Because the data we had no ability to detect precipitation, but surface water content or water cycle means plant water content or such a parameter. So I think it is a capability to combinational use of the water product in the land surface and methane or CO2 product.
Yeah, thank you.
Any more questions?
I was very curious, right? Like maybe looking forward, as we look at all these data sets and the measurements we're doing, how do you think we can bring them together to measure some of the mitigation or removal programs that will be rolled out? And so one of the areas I've been looking into a lot is ocean-based carbon capture and ocean alkalinity stuff, where just the measurement itself is impossible right now. And so I'm just curious, like as you look at your individual research and kind of data sets, how do you see it coming together for actually tracking and enabling progress on the mitigation or removal or adaptation side?
And I can...
Yeah, that was actually the whole point of my presentation. So under the World Meteorological Organization, which is the UN body, we are working together with the modeling centers of the member countries, and we are working together with the observational community to put it up on the system, which would be pretty similar to, let's say, numerical weather prediction, where you don't think about it. It's like it's there. You go to Weather Channel and you get your temperature in any region in the world. So we wanted to have similar system for greenhouse gases, like looking at the fluxes of greenhouse gases, but coming from, let's say, several centers. So we have much better understanding of the uncertainty of the product. So we compare like a multi-model product, which will be produced on a monthly basis. So you will have a net flux of methane and CO2, potentially N2O with a resolution of 1 by 1 degree. And you've heard that such products already do exist. So under the umbrella of World Meteorological Organization, we wanted those products to be made available fast and on a sustained basis, just like weather. So you would look on the website and see what is the flux for the last month. And using this product, of course, you can see if there are declared mitigation actions and you don't see any response in the atmosphere, then there are two answers to that the actions hasn't been taken at all, or that the actions are actually not working the way you expect them to work, because you plan to, for example, work on a large-scale agricultural practices, and you change your practices, but there is something like a climate feedback, right? So you reduce the supply of the fertilizer, but the temperature has increased, so you have an offset just from the climate variability or response to climate change to your N2O emissions. So that product would help everybody to see what happens on a global scale. Of course, you would need to do the downscaling to get a whole cascade of the tailored products, but the global net fluxes will be made available, and we are planning to develop such a system by the second global stocktake.
Thank you.
Any more questions? Oh, yes, in the back. Yes, go ahead.
Hi, my name is Julia Sadana, and I had a question about the new capabilities that the GOSAT will have. I was wondering if you could speak a bit more about how it fits into the current ecosystem of instruments that can measure and detect methane already. And in particular, I was wondering about what Paul Palmer was mentioning, that if we are having these huge emissions coming from East Africa, and it's already difficult to see methane emissions, or at least identify the source in that region, because there's all this, at least the human-related sources, because there's this variability introduced by the emissions from the wetlands. I was wondering if you could speak a bit as to whether those capabilities would make it easier to perhaps isolate those sources, or would it just become harder to see, to try to pinpoint what is the emission source, or what are the human-related emission sources in that area, with that increase in the natural emissions as well.
GOSAT thread itself observe total SGH4, so we cannot, observation itself cannot recognize it is natural or anthropogenic, so we need to modeling framework to separate natural and anthropogenic emissions. So for that reason, we produce L4 products, and lots of researchers do the research work for inversion analysis like Palmer introduced. So in such a collaborative work is important for the future analysis for CH4 cycle and contribute to the methane pH. How about?
I can actually add to that. When we have a discussion, we need to put it in the context, and we need to talk in the context of the integrated observing system. So one system potentially will not answer all the questions, but if you supplement the satellite observation with ground-based observations, and on the ground you could measure not just the concentration of methane, but also, for example, isotopic composition of methane, then this additional information, isotopic composition, can actually help you to distinguish what type of methane is coming from the, let's say, biogenic activities, and what kind of methane is coming from the anthropogenic activities, or thermogenic, we call it thermogenic methane. So complementing two systems will provide you a lot of clues. So just looking at the one source is not super efficient. That's why you need a combination of both. And unfortunately, if you look at Africa, there's hardly any measurements of greenhouse gases on the ground, which actually prevents us from understanding what is going on with the carbon cycle in that part of the world.
So this, probably you have anything to say? Yeah, go, yeah, quickly, go. Sure.
So this is a question for George Hart. So I actually very impressed to see the above ground biomass you estimate from your JD system, and the bottom-up flux, the above ground biomass. But there I saw there's some differences for Indonesia or Canada where your lines are not like the observations or your estimations does not fall on the one-to-one line. But for Brazil, US, that looks very good. So are there challenges to whether Indonesia or Canada are not really falling on the line? Or what are the problems or challenges remaining in that above ground biomass estimations? And what are the prospects for the flux estimation from your calculations? Did you touch upon a little bit, but I'm curious to hear. Did you get?
Yeah, I think thank you for that question. I think I heard you were asking about that validation we do against different national scale reporting. As that overall, I think the conclusion from that slide is that most countries' reporting is consistent with these new space-based observations we have. There are some countries that are off that one-to-one line, and we're in the process right now of investigating why that is the case. So I don't have a definitive explanation for that at this time. The second part of your question was about fluxes. Could you repeat that part of it?
I mean, what are the prospects of converting this above ground biomass and their changes to the fluxes with time or with year or with decades?
Yeah, absolutely. So this model produces flux estimates too, and I know I was going through that pretty fast, but we gave an example of the 1 year and also 1 kilometer net fluxes in that same slide. So once we initialize this model with these LiDAR observations, we can produce the biomass map, but use the corresponding components. One is that the spatial resolution high. These are 1 kilometer global land atmosphere fluxes, and I think that's unprecedented. But then we have that same capability rolling forward as that subsequent slide showed. Under different scenarios of future climate and land use, we can see what those fluxes would be at that same spatial resolution for a century. So I think it's very exciting.
Great. Thanks for questions. But don't forget, I have some questions already to ask for speakers, so maybe you can do that remaining 10 minutes. So the main theme today's session is Earth observations in support of mitigation actions for the Paris climate goals and SDGs, right? So our question as an organizer to panelists and the audience is like, what is major challenges for using Earth observations for applications from in your past experience? And also, what is new areas that you think Earth observations can be used for climate mitigation? And if you have any thoughts on these, then we would appreciate to hear and then discuss further with the audience. So maybe George, you have any thoughts on that already or not? Maybe not, but George, did you hear me? Yes.
Sure, I will, yes, I think I did. Thank you. Well, I think we're in this unprecedented time where Earth observation can improve our understanding of the global carbon cycle, both past, present, and when we couple it with models in the future. And the NASA Carbon Monitoring System is prototyping these opportunities in every aspect of the carbon cycle. The example I focused on today was terrestrial carbon fluxes, because those are one of the largest and one of the most uncertain terms in the global carbon cycle. And we benefit right now tremendously from a carbon sink, which offsets something like 30% of fossil fuel emissions. And we really don't have a good understanding of where and that is, and what the processes controlling it are, and whether or not it will continue in the future. So I think that's one of the most important places to focus, and a place where Earth observations are making a qualitative difference through LiDAR and radar in particular. Thank you.
Panelists, anything to say? Or yes, Oksana, go ahead.
Yeah, probably I will be again repeating what I said, is that there are the limitations in the satellite observing system which we need to recognize. So we need to be pretty clear that there are some areas where it will be very difficult for satellites actually to work. For example, when there is no light, polar regions, which will be not covered by observation, the satellite observations, because you need light. There are tropical regions which are under clouds, which created also a lot of difficulties to use the satellite observing system. And also how frequent you can do the measurements. If you have one, like we've seen that there are some satellite systems which do the overflight over the globe within 3 days. So each and every single point is not observed all the time. But also there is a challenge in making sure that there is a consistency between satellite systems, because it is pretty difficult and expensive to launch the satellite system, and chapeau to satellite agencies who are actually doing this long-term planning. It's 10 years planning upfront for the upcoming missions, and you need to make sure that the new missions are intercompared and calibrated versus old missions, and you need to make sure that they measure the same variables so you can have a consistent data sets, especially when it comes to the operational system. It is a huge challenge, right? So given these limitations, again, we need to look at the integrated systems where we have both segments proportionally developed, like TCON, which is used for the calibration of the satellite system. We need to make sure that it's sustained and it is placed in many more locations so that you have a reference on the ground for the upcoming missions where you can actually make sure the consistent data sets. Regarding opportunities, satellites are becoming better and better, and they can measure more and more parameters which are relevant to carbon cycle and which are relevant to attribution of greenhouse gas fluxes, integrated approaches, air quality, and climate. And many of those opportunities are untapped. And given that we are coming to the era of new computing, artificial intelligence, quantum computing, I think that there is a huge potential to utilize much more satellite data from the different points of view and different variables. Of course, if we can transmit them on the ground, which will be another challenge to overcome.
Yeah, thanks. These are important points in terms of science and techniques, or technology, I think. But I like the point that, as Oksana's presentation, you mentioned like a capacity, a manpower thing. I think that's also really challenging, and also current challenge, and also we need more capacity in terms of data applications or data analysis in making more opportunities happening in the future. So anyone in panelists, if you have anything to say, that's welcome.
Oksana's provided a very comprehensive description of what's going on. So, but I think to summarize is that we have to integrate large volumes of heterogeneous data. So we have land surface data, George's been talking about that, we have the in situ data, the ground-based data, and the satellite data, and the volumes involved now are just going to grow with time, and so absolutely AI is going to play a key role here, provided there's enough domain-level expertise to support the use of AI, because we always forget that bit. There still needs to be domain-level expertise. The only other thing I would like to stress is that, I talked about Africa. I've never been to this place. I think that, developing that capacity for local scientists to collect data and interpret their own data, that would be great. I'd like to see that more and more as we go forward in time.
Yes, yes, that's a good point. So, anyone from panelists or even audience, any thoughts are welcome.
I have a question.
Sure.
So we talked about the more science and the application, but we are developing a lot of useful sciences. But at the end of the day, we need to apply to the society. I just wanted curious, George, specifically, you have a lot of experience with engaging with stakeholders. What is actually the challenges? Not like scientific, but communication is so important, for example. It would be great to have your thoughts on that.
Yeah, I can say that Jocelyn is in the audience. She's a co-chair of the Integrated Global Greenhouse Gas Information System, and in IGIS we have the user engagement strategy. And when we talk about user engagement, we actually do not understand the whole spectrum of who are the users. And the understanding of the product by the user is completely different from what we say as a scientific community. And I just can give you like a very easy and intuitive example. The user may say, I have my rice field and I change the watering cycle on my rice field. Am I a source or am I a sink? We as a scientist need to convert it into the technical requirements to the analytical system. Then we need to convert it into the technical capabilities. And then you need to understand that when you come up with a model output, you need to convert this model output into the information which is digestible to the user community. And this is just one example. I mean, the whole spectrum of the user community, if you talk to the mayor of the city, who needs to have a urban strategy for emission reduction, or if you talk to the national negotiator who negotiates NDCs, it's completely different. So we as a scientific community oftentimes don't understand the language of the user community, and conducting those user consultation is also pretty difficult because the users oftentimes not interested in participating in those discussions because they don't understand what we are talking about.
Yeah, go ahead.
Maybe George? You want to add something, George?
Yeah, sure. I agree with what Oksana was saying. At the NASA Carbon Monitoring System, we've prototyped over 100 different projects doing carbon monitoring research, and every one of them pairs with one or more stakeholders in their projects. I think one of the key lessons we've learned and tried to implement in our system is what we call end-to-end co-production of information. So we've tried to really blur the distinction between the scientists and the stakeholders and get them collaborating on day one of their projects. We found this to be so important in making sure that the science products actually meet the user need, and also so that the users understand and believe the science products they're getting. So I think this end-to-end co-production is probably the single most important lesson we've had.
I think we all agree on that, and that's never-ending discussion, I think. So it's just keep going, keep in touch, and reminding each other, and then maybe you can see next COP and getting a little bit of better idea on moving forward. Okay, I think now we should close the session, and we're going to have a closing remark, which, which Tom is going to be introducing.
Right. Thank you, everyone. So now, pleasure to introduce our USLA's President and CEO for addressing closing remarks. Dr. Dick Isaacson.
Thank you, Tom. Let's have a round of applause one more time for our panelists. Did a great job today. What we've seen and heard here this afternoon and now this evening shows just how important Earth remote sensing is to measuring and monitoring our atmosphere and mitigating the effects of climate change. We've also seen the importance of international collaboration on the difficult challenges that we face, such as these. These two things, scientific discovery and collaboration, are really founding values of the University Space Research Association, USRA. Established in 1969 at the height of what we may now think of as the first space age, we are a nonprofit international association of 117 universities and growing, working at the leading edge of space research. We were proudly admitted as an observer NGO in 2021 and sent our first delegation to COP26 in Glasgow. We have a long history of research and development in virtually all fields of space science and engineering, Earth science being just one. And we continually assess how we can contribute to the ongoing challenges of climate change and through our scientific efforts inform the policy discourse now facing all nations. We do this through the work of our own scientists and engineers, but also through the partnerships we foster in the United States and around the world. I am hopeful at the progress being made, and I believe that Earth remote sensing will be even more important in the years ahead. But it's also important, I think, that we continue to innovate in such areas as sensor design, modeling, data science, algorithms. There have been important actions on reducing methane levels at this conference. Here's an opportunity for all of us, doing science from space to do more right now. And that may sound obvious, to those of us in the scientific community, but I assure you that it's not obvious to everyone. And I think it's really important that this community be vigilant about sending that message. So in closing, I would like to thank the National Institute for Environmental Studies and all the organizers of this event. Let's keep this important dialogue alive and our good progress to date continuing forward. And finally, thanks to all of you in the audience and online for your participation and engagement in this event. Well done.